Okay, test. Should be live. Hello, everyone. Welcome back to the stream. If you're here this evening, it means you have chosen to watch this instead of watching GDQ, a choice I do not understand, but that I really appreciate. So, what news? I missed the stream on Thursday last week, sorry about that. No big news about the project as a whole. I think last week we made a lot of progress on function analysis and on cleaning the analysis file, which means hopefully this week we can make some good progress on that and finally move on from this analysis phase and move on to maybe the lowering into AR and the control flow analysis, that kind of things. And that's about it in terms of the project. Oh no, another thing is I've joined last week. I think I mentioned it on stream. There's a small group of us people who stream in functional or declarative languages at declarative.tv. Small group, like not a professional thing. None of us is paid for this, but like, you know, if you enjoy watching me do stuff in Haskell, there are other people doing stuff in functional and declarative languages. You can go have a look at the list and find other streamers who do that kind of stuff. And we have a small Discord with a channel dedicated to each streamer. So if you want to ask questions about this project outside of the streams, that's a perfect place to do that. So yeah, declarative.tv. Otherwise, yeah, nothing big happening. I guess we should just get into it. So, last time we did a lot of work. Let me switch to this view on cleaning up the way function calls, and we did finish last time with being able to test function calls, including testing function calls with like partially given type arguments to make sure that we could figure out like, okay, we can deduce the type of this based on the function arguments. So this type checks, we figured that out last time. As a result, we finished this nonsense here, which is the analysis of a call expression in the context of a function. Now, what I'm hoping to do this week is to make progress on the remaining of this function, everything that's commented out here, as in all the kinds of expressions we might encounter in a function, because when that's done, we can move on to actually doing analysis of statements, because so far we only do continue, break, and return, and that's about it. So we can start doing if, while, and so on, and to check that those are correct. And with that done, hopefully by some point next week, our analysis phase will be finished, which will be big progress, which will be nice. There was something else I meant to also mention regarding function calls. Yes, there's something we're going to need to do as well that we haven't done yet. As a reminder, the way I am thinking about doing instantiation of generic functions is to do the same thing as C++. We don't have traits in this language, so I cannot constrain a generic function to be like, oh, for any type T that happens to be a container, or happens to be a number, or something like this. So I'm doing the same strategy as C++, which is like that function is defined for any type T, and we do whatever we want on the type. Type checking is not done when we analyze the generic function. However, when it is instantiated, we try to substitute the types and we create a new function that is the expanded version, and there we do the type checking. So that means at the moment there is a lot of like special cases in this handling of expressions and functions where if we encounter something that is based on a generic type, we just decide, hey, this type checks for now, we'll check later. So we need at some point to have a way of doing this kind of instantiation to be able to, at a later point, generate the actual functions and type check them. We don't have that yet. We could start. I'm going to be tempted. We'll see when we get there. When we actually finish the function analysis, I'll be tempted to skip this function instantiation thing, just because it means we can move on to try to actually do the AR and everything with just regular non-generic functions, which allows us to get something that we can actually, compile and test, try to finish one full loop of the program, rather than spend more time on analysis things when we've spent months on it. At the same time, I feel like it would be a shame to not have something that's a bit more complete before moving on with the rest of the things. So I'll have to think about it. But for now, let's continue the analysis. So last time we finished call expressions. with this to do here to register functions for instantiation. We added at the last minute that, yeah, literal expressions do not need any analysis. Is that true, actually? Is that true? I guess it's not. I guess this is where, if I had information about the target of the backend, for instance, am I targeting a Piètre interpreter that only works with 32-bit integers? This is where I could decide that no, actually, this int literal doesn't fit into the definition of a literal and therefore cannot be a valid one. But I don't think we really need that kind of checks at the moment. I think that's really beyond the point. So I'm not going to bother with that. For now, an int literal, a boolean literal, a character literal, that's just what they are. There's no need to do any kind of analysis on them. They're fine. String literals we don't support yet because the support for vectors and for arbitrary sized types is not done yet. So that's something that we don't have to do yet. Likewise, for array expression, index expressions, that's something we don't support yet. So for now, this can remain completely undefined, which is horrible, but, you know, easy to grep in the code to find things that are not implemented yet. But I think we could do a struct expression. So, a struct expression is a constructor for a structure. So the thing on the left here should be the name of, like, the type name of a struct, and here are the fields that must be given as an argument. We've already done something extremely similar in the context of constants, so we can probably duplicate most of the code from there, although there might be some subtleties given the fact that there are more things allowed in functions that are in constants. So let me do two things. First, I'm going to open the AST here so that I have a reference for what an expression is. Struct expression, where are you? There we go. This is therefore a path info, which is the path to the type name, and a non-empty list of identifier and field, because in this language, structs cannot be empty. Okay. So let's go see what we do for a struct expression for a constant, which I think this is. It is indeed. We try to resolve a struct type. Okay. Which gives us a bunch of things. We resolve the fields, that makes sense. And then we have this analyze struct fields function. I'm going to copy this for now. And we'll see what needs to change in the context of the function. Oh, this is already what's in there. Perfect. So, just to have a check, resolve struct is part of our resolving functions in context here. And resolve struct, if I remember correctly, where are you? So it takes a path that is passed and will resolve it as a type. So to make sure that this is indeed a type name. So if it is a type alias, will actually give us the actual type pointed to by the type alias while doing type argument substitutions. So it gives us the full path of it is this actual concrete type with those type arguments. And then we'll call a check struct type, which is this thing here that will check that indeed the type that we have, an actual type, is not an enum or a built-in type, but a struct. And we'll extract some information out of this struct info. And will give us, as a result, the path to the actual type, the information about the struct, and a hash map from type argument to the corresponding types, if any. Could be just placeholder in some cases if we don't have anything else. Okay. So that should be the same. There should not be any difference here, so this should remain the same. what I'm interested about is this analyze struct fields function, because I know last time we found some issues that stemmed from the fact that this was made only for constants, and therefore there were some things we were doing wrong. And I think this was about. This was if we were providing a placeholder for a type argument, we were doing something wrong. Can I remember what it was exactly? By looking at what we've done for functions? I think this was that the type diff. Yeah, there we go. This is what it was, where we after doing the diff of all the types in what was given to us, what we found in the fields, we do a union with the mappings that were given to us from the call, so that we don't ignore it. Do we do the same thing for struct fields? Let's see. We do indeed. So we fixed that problem. So I think this should be fine. The only thing I'm not sure about is this might be, in a case of constants, since all of the values have to be known at compile time, we do constant unfolding. We inline all of the values of the constant. I'm not sure we actually do that in the context of well, I'm not sure we cannot do that in the context of a function, and I'm not sure how much of this we do in the context here. So maybe here we're gonna need to change this function to not do inlining in the case of in the case of a function. Let me see. So we take as argument the struct info, the mapping, so everything that we already have even in the context of a function, and with the typed expression of the fields, okay. And I think, okay, so the only thing this gives us is the resolved path info to the struct. Is that because at the end, yes, okay, given what we know about the type parameters, we must be able to resolve all of them. This is where maybe something is going to be wrong, because here we need to accept that some types will not be known if they are type arguments that we don't know yet at this stage, because again, with the way we deal with generic functions. I think otherwise, if this is handled by this piece of code, then, which I think will be fine, because we do a types all match on this list of possible types, which means if we end up with like, oh, the type of this field must match the t and u type parameters of a generic function, it means that, yeah, the generic function must be called with type t and u that happen to be the same, but otherwise there's no problem there, so that should be fine. Most specific type, however, might be a problem. No, it should be fine. Okay, it is a total function. It doesn't have any error. Like, it will not panic in case of a problem because it's dealing with a non-empty list. So that should always work regardless. That's fine. That's good. So let's go back to struct fields. And so at the end, this gives me the actual proper type name with all, but it doesn't tell me anything else, which is good. So we can use it here. Yeah, I think this is already correct. That is a typed expression of this fully resolved type, which happens to be a struct expression. We did not do any inlining there. There's no need to. The inlining will happen in the case of a field access expression if the struct expression is known at compile time. And it's a fully resolved type and the resolved fields. Yeah, okay, so I think this is exactly the same as we have for constants. So we don't need to add anything else, which is always nice. We can move on to reference expressions. Reference expressions are very, very specific because, given the way the language are defined, they can only happen in one place, which is in the argument to a function. And they are only used to basically give a hint to the compiler, like, hey, this argument should be like just, rather than making a copy on top of the stack, we should just move the stack so that the argument is actually given directly to the thing and then copied back after the function. But we cannot create variables that contain references. We cannot like use references at the type level. This is purely for arguments, so it's a very, very restricted thing. This is one of the many, many liberties we have taken with this language, where we have a much simpler thing than what the actual Rust language supports. So here, I think we don't need to check anything complicated because those can only appear as per the grammar of the language in a very specific context, and they are going to be checked as part of the process of checking function arguments, which we did last time. And I use function arguments here, and it's basically like, am I passing something by reference? Did I get a reference expression? That's about it. Which means, since reference expressions can only be created in that context, there's nothing to check here. This will be checked for the function call. And here, the only thing we have to do is, given some expression, this is going to be a reference expression applied on a, how is this function called? Analyze function expression. Okay. Of the actual expression underneath, and we wrap, I can't do that actually. Can I? Or can I? No, I can do that because the result of this will be a typed expression which contains the type. The type will not be modified since reference expressions are very peculiar. Again, they're not part of the type system at all. So we just need to apply this to the inner expression. Is typed expression, is that a functor? Can I do that? And even if I could, this would be an fmap of fmap, basically. Let's see. Let's do that. Let's go to typed expression, which is this. I did not make it a functor. Do I want to? Do I want to? No, I cannot. That makes no sense because there's no. This is not generic over this thing. I can't make it a functor. So I could make a custom map function for this, but like that purely only accepts endomorphism on expressions. But that feels kind of useless. Rather, I am gonna do this instead, where I get a typed expression that I unwrap here by doing this. And what I create based on this is a new typed expression that shares the expression type, because the type is the same. Because references are dealt with accordingly just for function calls, so we don't need to have references at the type level, which is nice. And the actual inner value will be not just the actual expression underneath. How is it called? This is type and expert value. It will be a reference expression of the expert value. There we go. Okay. That should be all for references. That should be all that we need to do. Then I am not sure what this command does. I'm sorry, I have not customized my Twitch quite a lot. I don't know what those commands are supposed to do. But if you have like suggestions for what those should do, I'd be happy to add this in the future. But since you're asking, I'm working on a compiler project where I'm translating a language that is made up, which is basically a very, very small subset of Rust, almost exactly the same syntax, but slightly different and simpler semantics. No references or pointers or anything like this, for instance. No traits, like again, a much, much simpler language based on Rust. And we're compiling it not into an actual binary, although we'll do that at some point as like a side project. I'm compiling it to a esoteric language named Piètre, which is a language in which the source code is an image. It looks like this. This was generated by our project, but not yet fully with a full compiler because the full compiler doesn't exist. It was generated with only the backend part of the program. And this small Piètre program just prints 2 characters and exits. It doesn't do anything fancy, but the goal is to, at the end, take some Rust-like code and translate it into images like this. But taking it as seriously as I would if I were to write an actual real compiler for a real language, which is why, despite the fact that like we are making some things a bit simpler, again, no reference types, no trait, no anything like this, I'm still trying to take it extremely seriously, which is why we have generic functions, generic like types, and so on in the language, because I want this to be a real compiler, even if the goal is kind of silly. So that's the project. And today I am still, like, I started a few months ago at this point, and I'm slowly making progress. This list here is not super up to date, but yeah, the Lexer parser already done. What I've called the linker and assembly, basically, if we have the bytecode that correspond to instructions in the Piètre language, basically taking a bunch of functions that have references to other functions by name and then assembling them, like linking them in a way that we assign a unique address in memory to each of them. That's done. And then the assembly of generating an image from each of those functions to make a composite image, that's already done as well. At the moment, I'm trying to finish the analysis part, where we take what has been passed and we do name checking, type checking, and all of those things to make sure that the program is correct. And when that's done, we can move on to the IR generation, where we'll try to do an IR that's like going to be based on the LLVM one, although a tiny bit simpler. And at the end, code generation to generate the bytecode. Yeah, it is kind of my goal. Like I want this to be like, I'm saying I'm taking it as seriously as I would a real compiler. It is the reason I've been using Alex and Happy, which are the Haskell equivalent of like Lex, Yak, and other things like this in other languages, because I want this to be as close as possible to real compiler in terms of structure as I can, because I think there's like value in terms of like it being somewhat of an educational project. Although it's gonna be a long one. I'm uploading every stream to YouTube, but like again, it's been several months of work, and there's several months left to get it to a point where we can even generate one image. But yeah, it's the project. At the moment, specifically today, I am going through this gigantic function, which is we have a passed expression in the context of a function, and we have to name check it, type check it, check that it is valid. We've just finished doing checking extract expression, but that was a bit easy because we've already done that in the context of an expression in a constant, where those can happen, and therefore the code is the same. We've done references. I've said the language doesn't have references. It has a somewhat similar thing just for function arguments, so that was not too complicated. Time to move on to some other things that we need to check for expressions in the context of a function. As we have here bool negation and int negation, which are, as you might expect, exclamation point and the minus, of course, which can appear in expressions. Yeah, if you have any question about Haskell, I'm always happy to try to answer them. When I do my Advent of Code streams, I try to keep it to like very beginner-friendly Haskell. With this project, it's not always possible. The code is big, but if you have Haskell questions, I'm always happy to take the time to answer them. One of my goals with this project, with all of my projects on Twitch, my Advent of Code stuff and everything, is to try to help showcase the fact that Haskell is not as complicated as people might think. It is a very practical language used for practical things. It has a bad reputation just because it is a different language, but it is not actually that complicated. So again, if you have Haskell questions, do not hesitate. I am always happy to take the time. But here, so we have to check that a Boolean negation expression is correct. This that I have copied here comes from the constant thing where we do this. But for a constant, things are a lot easier because we know the value at compile time. So we can check, do we have a Boolean expression? Yes. Do we have anything else? That's an error. We can report it. Perfect. However, things are going to be a tiny bit different here because we might not know the value at compile time. That's the whole point of functions. So here we are going to have to deal with the fact that we could have something. Here we just need to check that the type of a random typed expression whose value is not known at compile time, we need to check that its type is still a Boolean thing, basically. This Boolean expression thing is a pattern alias that I have here. It matches to basically, this is a type expression of type Boolean that is a Boolean literal expression. So I guess we could just match this. Where was I? I was here. So if we match a typed expression of a Boolean type with a Boolean literal expression, then we can just return that, but not, basically. We can inline the constant at compile time. However, if we get something that is a Boolean, oh, I guess I don't want to do it this way because I still need to handle the fact that, again, this could be a generic function and we don't have traits, so we don't know yet what the generic type might be. So type checking must succeed if we don't know what the type is yet. So I think instead I'm going to do it in this case here. So we have a typed expression of a type T and some kind of expression E. And this is going to shadow this. I'm going to name it something else. Okay. Let's name things explicitly. This is a resolved type. This is a resolved expression. What do we do in this case? Put this like this so that's more readable. Here we have to check what the type is. And basically we only allow this to succeed if it is a Boolean type, or if it is a type argument, and therefore something that we cannot know yet. Let me just check what I have here. And Boolean type is itself a parameter alias, because this comes from name. No, it comes from built-in, actually. Boolean type is a path info that points to the built-in type Boolean with no arguments. So I guess here I need to check the type to be either, I need to check the role of the type basically to either the built-in type Boolean or to be, how do I do that? So I don't want to check, I don't want to do string comparison at this point. So I guess I could do, if I go back here, I can do a case resolved type of, I might not need to do here as a result. If I have Boolean type, which is an alias for the full thing, that's perfect. That's valid, but I cannot inline the thing like I could before. So instead, excuse me, I have to output, this is indeed a typed expression of a Boolean type. That is correct. And the resolved expression will be a Boolean negation expression of whatever the underlying resolved expression was. So nothing changes here. The AST doesn't get in line because we don't have enough information at compile time to do so. But we have checked that it is valid from a type perspective. Now, we have to handle the fact that sometimes we will not know what the type is at compilation time. And that means we might encounter, what's the only valid thing we might find? So this would be a path info constructor where the role is a type parameter. if we find this, that means that the type of this expression that we're getting is based on a type parameter. Actually, that is still not correct. No, it is. I was gonna say this is not the only case where we could have a type parameter. What if we have a type that we know parameterized by a type parameter that we don't? But we don't have associated types or type families in this language, which means foo of t or something like this can never resolve to Boolean because that's not a type, that we don't have associated types or type families, which means even if there is somewhere in this, like it's vector of t or something like this, or foo of t or whatever else, it will never be a Boolean. Even if it contains a type parameter, I can reject it, which means the only case we have to accept, because we cannot do type checking yet, is if this expression that is being returned is of a random type parameter that we don't know. So in this case, it means simply that trying to instantiate that function with a type parameter that is not Boolean will never work, but that's fine. So in this case, I also cannot do the type checking, but I can guarantee, however, that the result will be a Boolean. So for the benefit of further type checking, actually, do I want to propagate the type here? There's two options here. Either I say, oh, the result of this expression will be a Boolean because a negation expression will always return a Boolean, regardless of the context in which we are, which means we might surface type errors a lot earlier than we might have otherwise. Or I can say, nope, actually, this was given to me as an expression of this type parameter t that we don't know yet, even though we know from this context that it must be a Boolean. I'm going to propagate the fact that this is a parameter type t, so that if we find other errors later on, we might be able to give better errors. I am of two minds about this. I still think that since it must always return a Boolean, there's no situation where it might not. I think making this like, no, it gives up a Boolean so we can do early type checking even though we don't know all the types yet might be the right choice. Okay, so we do that. This is a typed expression of type Boolean, in which it's going to be the same thing. It is a Boolean negation expression of this resolved expression, and this will be type checked properly when we instantiate the function at a later stage. Okay? If we have literally anything else, any other type, this is where I should not have deleted the thing. Let's go back to Boolean negation expression in the case of a constant and copy the error we have used there. There we go. Any other case, this is a fatal error. Error wrong type. We were expecting a Boolean type, and what we got is this resolved type here. Let me just check what the type we expect for this error is. Let's have a look at diagnostic. Error wrong type. Path info resolved, that's perfect, that's what we have here. Okay, so that's typed, that's a Boolean negation expression. And for an int negation expression, that's going to be basically the same thing. So I'm going to copy that. I'm tempted to just do a Boolean int substitution. Let's see, let's check. So we resolved the exception go actually. It is called analyze function expression. There we go. We recursively analyze the sub-expression of this, and then we look at it. Is that an int literal? Do we know this value at compile time? Then perfect. We can return the negation of this literal value. Perfect. Otherwise, if it is not a literal, so not a value known at compile time, we look at the type. Oh, I guess I can write this differently, actually. rather than doing a case here, because I am redoing the case of like trying to check the type match. I already have a function for this. I could do instead unless type matches, and that's resolved type and Boolean type. Which means I don't duplicate the type checking logic. I delegate it to this one function that is the source of truth for all type checking things. There we go. And otherwise, if they succeed and we don't get a fatal error that short circuits the thing, then this is always going to be what we return. Let me go check type matches. Okay, it takes a path info resolved, which I think those are path info resolved. Perfect. So if placeholders, okay. If type parameter will return true, perfect. Void will be checked. That's a thing I didn't think of checking, so using the function is better because otherwise I would have missed this case. This is basically the type that is written only like Rust. I'm using the same semantics as Rust here. That's the type written by panic functions, basically things that cannot succeed. Which means if I have a branch that I know cannot succeed because it panics, type checking will succeed because, you know, it will always work on this. So, yep, that should be fine. Okay, so I can go back to what I was doing. I was scrolling past this and I'm realizing that my cast functions actually do not handle void types at all. I have to think about this. Will it make sense to have something that panics in a cast? Probably not. We probably don't need to handle this. I'll try to think about it. Okay, so let's go back to this. So this should be better. If the types don't match, and I'm actually gonna put it in an infix notation because I think it's better for this. There we go. Unless the type matches Boolean type, return an error. Otherwise, perfect. That is a typed expression of type Boolean, the expression being a Boolean negation expression of this. And for int, I think we can do the exact same thing. I'm gonna just copy this. And replace Boolean by int. Okay, perfect. Next, what do we have? Next, we have all of the addition, subtraction, and otherwise, like, and other int expressions. Addition was handled differently in the case of constants because I wanted to, at some point, be able to change it to handle string concatenation as well, which we don't need to handle for other operators. But we don't have strings yet, so... But I still probably want to, like, I've used this binary int expression otherwise. We can probably do the same thing here and use... Yeah, we can probably do the same thing here. So let me go take those comparison expression and binary bool expression. Let's copy all three of those from the constant part and change them to work for functions. There we go. We have binary int expression, binary bool expression, comparison expression. Okay. and compare expressions underneath. Let's copy all of this because it's gonna have to be different. And let's put it here. Nah. So here, what do we have? We have the same thing we have before. We are dealing with a binary int expression, so like minus, division, plus, something like this, except plus will be handled differently again. But here, this was written with the assumption that we would know all of the values at compile time because this was for the case of expressions, for constants, where everything is at compile time. So here we need to change this to handle cases where we don't know the value at compile time. So first, Go doesn't exist in this context. This is analyze function expression. And I don't think we can do that because again, yeah, what we're going to need to do is to check that both of them, yeah, we're going to have to do something very similar to what we've been doing here. So instead, I'm going to remove all of this. I'm going to copy it in a comment just to see what we were doing. Because I think what we need to do is basically the same thing as what we're doing here, which is in the case where we have two int expressions, we can return like if we know both of those values at compile time, it's very easy. We can apply the operator f on those two things. F being here the argument we give, which is a function from to int to an int. So we can compute the value at compile time. Interestingly, however, I have just realized that in neither the constants nor this do we handle division by 0 at all. So I think if I go back to this and my test function and I try to do, let's do a constant O knows of type int and it happens to be 3 divided by 0, this is not going to be an error reported to the user. This is going to be a crash of our program. Instead, I am fairly certain. Let's try. Yep, divide by 0. There we go. That's broken. Okay, well, adding something to the stack, we're going to fix this. Okay, so how do I fix this? I guess I could just add like a validation function here, which can be nothing for all of the other values. Or this could be that instead, the function here that does the operation returns something in the analysis monad and therefore can report an error, and maybe that's better that way. Yeah, okay. Okay, so if we do that, then this is no longer this, it is this. Because the f function returns something in the analysis monad, and we fmap int expression to it. Okay? Which means we only get an int expression on success. Except this is not here, this is here. Okay? And we can do the exact same thing if instead we get literally anything else, then we can do this kind of type matches, which will be more difficult for the case of strings because we'll have to check that both types match regardless of whether they're ints or not, because we will want to support string concatenation as well. But for other things, it's going to be as simple as doing this. So this will be checking. So this is going to be the expression type of the left-hand side needs to match in type. Otherwise, I'm not going to use fail here. Let's go back at the monad and look at how we have validate. We have report, abort. Wait, how is fatal defined? Is it part of... Yes, it's part of this. So it's basically report and abort. Okay, so we're gonna do instead is report here, so that it's not a fatal error, so that we can get errors for both right-hand side and left-hand side at the same time if they're both wrong. And then we validate so that if any of those two things was an error, we then short circuit, but with both errors rather than short circuiting on the first one and ignoring the second. Okay? There's probably something better to do with error handling. Because there's a bunch of places where, like, here, if it fails on the left-hand side, we're never going to try to analyze the right-hand side. Which means there's a bunch of errors we will not get on the first compilation. I'm sure there's a way to do better than this with error handling. What could we do instead? Maybe I could try, in all of those cases, I do a try on the left-hand side, right-hand side, and then I would need to have a function that, given a maybe thing that was basically gives me the value, otherwise throws an error, so I can then... I'll have to think about it. I think what we have at the moment is not good enough. I mean, we know that it's not good enough, but I have to think of ways to make error reporting better. Okay, so here we've checked that even if we don't know the value at compile time, the types both match int, therefore doing the operation is valid, and we cannot inline the value, so we can't use f here. Oh, I will need to check that the int is not 0 for, like, division and stuff, but this will probably be handled at the... This will probably be handled at the code generation phase, where, like, okay, here we have a division. The bytecode we generate for this is bytecode that checks that the dividend is not 0 and panics otherwise. So this is not something we do as part of this. However, here we are going to need to know the constructor that we need, which is going to be... Where's expression? There we go. Yeah, it's something that basically, given a two types expression, give me a new typed expression. So this one is for the case where we can compute the value at compile time. This one is for the case where we cannot. So it's going to be C, the constructor, I guess. So this will be pure, well, yeah, C of LHS, RHS, I think. Yeah, that's all it's going to be. Okay. And yeah, we've reported, yes, okay, perfect. So now for a binary Boolean expression is going to be the same thing. I am going to need the same way to construct the same constructor thing here. And otherwise, I think this is going to be the exact same thing, but with Boolean instead of int. GHC up. So sorry, I should get into the habit of reading the question out loud for people who watch this on YouTube. So are GHC up, and Cabal the way to go? That's a can of worms, but it is not a wrong way to go about it. Yes, using GHC up to install like your system-wide install of like all of the Haskell tools. Yes, that is the recommended way to go about it. As for project management, some people still prefer Stack to this day, but there's a lot of debate there. Stack was introduced at a time where Cabal was not as good as it is today. Nowadays, it's less required. There's been a lot of work done on Cabal. But yes, for system-wide install of like which version of GHC you want install, which version of Cabal you want install, yes, GHC up is the way to go. And again, then it depends for your actual project. Do you want to use Stack? Do you want to use like Cabal directly? Completely up to you. You can even do something a bit in between by using the how is it called? Is it called HPAC? The thing that basically allows you to use the YAML file format that Stack uses without using Stack and just like generating your Cabal files once and for all. I think it's called HPAC, but I'm not sure. But yes, GHC up, GHC Cabal, you wouldn't be wrong with this. The big thing about Stack is that, and they still do it, basically, when you use Stack, you can set a specific resolver version, and all the packages you download are for that specific version. And they have a thing running regularly where they test all the versions of packages at the same time. So if you use Resolver 3.25 or whatever, you are guaranteed that all of the dependencies you pull are compatible with one another. You will never get into a situation where like several of the dependencies depend on two different versions of the third package. Like all of the dependencies work together. You avoid any dependency issues. That's a big plus of Stack. My personal thing, which I'm not saying is the right thing to do, is just what I tend to prefer. I like to use Stack for binaries when I'm making a program because then I avoid all of this dependency thing, and just use raw Cabal directly when I'm making a library that other people are going to use, because then they have the choice to use Stack or not, whether they want it or not. Like I'm not tied to specific versions of the library as much as I am for a binary. For binary, I want very specific versions. I'm using Stack. For a library where I want this to be as generic as possible, I'm using Cabal directly. But again, there is no wrong way to go about this in this situation. So here, yes, I just want to replace int with boolean for this, and that should be fine. Because yes, if we know the boolean expressions at compile time, we can apply the function at compile time. And here, there's never going to be a need to check the values. There is no value that might return an error, so there's no need to handle this in the monad. So a directly boolean to boolean function is fine. So this fmap can stay. Oh, actually, no, it needs to go. It needs to be like this. Because the value will be known directly, not in the monad. Oh, wait. This is not LHS, LHS, this is L and R. The values here and here. Likewise here. And otherwise, we check that both sides are a Boolean, or at least will potentially be a Boolean. We validate, and we return the constructed version. Okay, that's fine as well. That's for a comparison expression. What do we do here? Hmm. I see. Okay. So what we do here is we do, I think, basically the same thing that we will want to do. Oh, but that's going to be a tiny bit more complicated by the fact that we don't know the values at compile time necessarily. So this is what we do at compile time for constants, which is we check that they are the same type, and then afterwards we compare them pairwise. Like, we have this struct on the left hand side, this struct on the right hand side. We have this int literal on the left hand side, this int literal on the right hand side, and we try to compare them pairwise and make sure that all of the comparison, like we do an end of all of the comparisons, basically. Hmm. But how do we do this on an expression that might not be known at compile time? How much can we inline, basically? Well, if we have two literals, we can always inline. We have two structs. If we have two structs, we could rewrite this. If we have a struct expression, that means the struct expression is known at compile time. What we could do, I suppose, is basically if we know that this is a struct expression at compile time, then we can replace it by a series of ends, basically, except or ors, depending. No, ends actually, because we're doing a comparison on the fields, and we inline the ones for which we know the answer at compile time to only keep the ones for which we don't know. So if we have two struct expressions, which means we know those struct values at compile time, but we might not know the fields, we can translate that into a series of AND calls, basically. Otherwise, we just have to emit. Yeah, I think this is what we have to do. Okay. So we change this. I'm going to need the constructor again. This one. Likewise here. Okay, how do we do this? So we've checked that the types report is no longer the function. This is fatal now. Okay. Okay, yeah, that should be fine. So here we are gonna do a pairwise comparison of the expressions. The big difference here is that at compile time, if we don't get things that match, it just means that one of those two things, it just is just not known at compile time, which means the default case is no longer impossible, it is in fact very likely, and the default case will therefore be this. We call the constructor here, which is here, which I need to give here as well, to create something out of the, oh, we don't have a typed expression. Which means I suppose that those two need to be typed expression instead. Because we might need, unless I use the actual expressions because I'm doing the inlining, and therefore instead of a constructor here, I take the actual type expression, which is my default case, basically. There we go. And here, as a result, this default case is C of... Here, I'm still going to deconstruct them because it's useful to do so, but give a name to the thing. And in the case here, the default case is just this constructor called on the left-hand side and the right-hand side. Okay. So that is the case if we can't do anything better at compile time. But if we can, so here that means we have the two values at compile time, we can return actually I don't need to get the full typed expression here because this is always going to be a typed expression of type Boolean. That's never going to be anything else. Comparing to things will always give me a Boolean. So in fact, I can probably have this return the expression resolved, which will be either an inline Boolean if we can, otherwise some kind of more complicated expression. And I know that the result of this will therefore be so simplified expression will be the result of comparing this. So I copy this and then remove this. And the result will always be a type expression of type Boolean with the result, which is the simplified expression. Okay. And so this is the default case, which is also an expression resolved. That's a lot of expression resolved. Wait. Yes, that's correct. Okay. Okay, so if we have any literal, int, character, boolean, we don't handle string literals here, but since we don't handle strings yet, that's fine. That is literally the result is applying the operator on this, which gives me a boolean value, which means the result of this is a boolean literal. Which is actually... Oh, this is not in the monad, because this cannot fail. Well, this can... Yeah, I don't think this can fail in a way that matters, because we've already done all the type checking. So yeah, that's what it is. Perfect. So pure here is not needed. This all here is not correct because we don't have all the values at compile time. This is, however, mostly correct. In the sense that we are gonna zip sorted. Oh, actually, I could have zipped with. Yeah, I'm gonna change. I'm gonna go change compare expression in the case of a constant. Here, I'm doing an all uncurry something. I could instead zip with compare expressions OP. Instead of creating a tuple and then uncurrying this function, I can just zip with the function directly, and this becomes an end instead. That's better. But here, it's going to be different anyway, so that's fine. We're going to need to remove this, because instead, what we're going to do is use this binary Boolean expression to deal with the fact that we have basically a bunch of end expressions of things, which will be inlined in the case where we have a bunch of Booleans. How do we guarantee, however, I don't think we want to do a simple fold. I think we have to do something a bit more complicated here. So this is no longer correct. What is certain is we have to do a zip with compare expressions using we don't have access to the default case for this. Let me think. Let me think for a second. What is the default case here? It will be something applied to the two typed expressions. Yeah, I'm gonna need typed expressions here. Oh no, actually, I'm extracting the expression value. Okay. But I need a way to construct the That's because I'm not doing any type checking on the fields because I've already type checked them. Give me a sec. I need to think about this. I think the simplest way to do so is to keep this like this, give it here as well, rather than the default case, and take typed expression everywhere, even if the result is not, it's just an expression, because we can always put Boolean type at the end here. That being said, no, we will want to do that here for the recursive case, so no, this is all typed expression everywhere. There we go. So this becomes that, no need to wrap the result. We don't construct the default expression yet, we are just giving the argument here. Okay. So this also probably becomes a typed expression as well, which is going to be a bit repetitive, that's fine. That's fine, so here this becomes, we have the left-hand side, the right-hand side, and we are comparing, since we know the types match, we are comparing, there we go, okay. And the default case becomes, we apply C on the left-hand side and the right-hand side, okay. Okay, and now we can do something here. We sort on the first thing, and now we want to have a typed expression, so we do not do this, we just map on the second field. Now we can zip with compare expressions, the sorted LHS fields, and sorted right-hand side fields. So that gives me a list of the resulting typed expressions. What I want to do next is I want to partition that list between the values that are known at compile time and the ones that are not. I guess I could just do this with a fold, where basically I short circuit the second I encounter something that is false, and everything that is true I just ignore basically. And at the end, I construct a typed expression that is a bunch of end of. Yeah, I think that's what I want. Okay. So let's do this. Um, okay, and let's write this last function for this. Combine comparisons. Here we don't need any of the Boolean things here because we have already resolved all of that. What we have is a list of typed expression, and what we return is one typed expression. And I make it recursive, and I think I'm just gonna give it a top level parameter, which is a bit ugly, but rather than using a nested inner function, which is gonna start becoming a bit complicated. No, I don't. Let me think for a second. How do we do this? Because I basically want this function to short circuit the second we find something that is wrong, because if two fields are the same, we can immediately inline the whole thing with false and remove a bunch of runtime comparisons, basically. We can make it lazy, in a sense. Wait, can we? This is not correct. Oh, this is wrong. Oh, there's a bug in this. Okay, so let me show you what I mean. If I go back here and I remove this because I haven't compiled a new version that handles this yet, I'll leave it because I want to check that later. Let's try. I have a struct broken that contains a field y that is an int and a field x that is an int. Now, const broken is a boolean, and it is equal to broken of x is 0, y, x is 5, y is 5, less than broken x is 5 and y is 6. Here, this is broken because this is going to say true, I think. No, it's not. It's going to say true only if all of the fields here are less than all of those here. So the order doesn't matter. But in a lot of languages, this would be the order of the fields, as in if this one is lower than it's like basically treating the first field as most significant and the second field as less significant, basically, which we don't do here, I think. Let me try. If I open GHCI and I do data test ord, it contains 2int deriving equality and ord. Is test ord for 6 less than test ord 5 true? Because the 4 is more significant than the 6. But it is not greater. However, 6 4 would be greater than 5 because again we're treating it from like most significant to least significant. That is not how I've implemented comparison for structures in constant and how I was starting to implement them in the context of function expressions. So I need to change all of that. Okay. Let's do the usual thing we do in all of the streams. Let's stack more work on top of the thing that we're already doing. So this is all broken. That's bad news. But let's go fix it. So first, I'm gonna want to fix two things in the context of constants. In the context of constants, I will want to here make this as part of the analysis monad so that I can return an error in case something is wrong, which will prevent the divide by 0 from being broken at compile time. Which means we will need a new diagnostic. Error divide by 0, I suppose. And I don't think I don't need like type information or anything about this. This is purely gonna be like, hey, at this point, this thing here is dividing by 0. Okay. So we can fix this already, which will be fixed in this nonsense. Here, there we go. Those are the functions. So here, this is gonna need to be I could go the route of making this 0.3 by doing this, but I don't know if I want to do that because I would like to keep the code readable as much as possible, and I would argue that this might not be super readable. It's not the worst. It's not the worst. Yeah, I think I am tempted to keep it that way. And now for div mod, however, is where we need to introduce a new function. I want to create safe div. And actually, I might make it a helper common to all things because I'm going to need it as well for I'm going to need it for functions as well. So do I have a local helpers group? Yes, I do. Safe div is going to be given some, actually, let's go back to safe div. There we go. Given this, basically. Wait, no, not this. Oh yeah, I don't have to do the for all thing. It's always going to be on int only, so it's fine. So given a function from int to int, actually, make it into a function from int to, yeah, perfect. So safe div, given some function f and an argument x and an argument y, will be when y is 0, fatal divide by 0. How is it called? Error divide by 0. Perfect. And otherwise, we have checked this. It is now safe to do. Pure of fxy. Perfect. So now we fixed the crash in constants. That's good. But now we need to fix the error in struct comparison. Which is here. This is wrong. Okay. Because I sort on the name of the field, which is not the correct way to do this. The problem I have is I need to be able to distinguish here I need to basically be able to say, oh, those two values are the same, therefore they're not enough to answer this, and I need to continue. Or, no, those two values are enough to decide, therefore I can stop here, basically. Hmm. Wait, I could cheat. I can cheat in the constant case. I can't cheat in the function case. Because I can cheat in the constant case by using the fact that I have all the values at constant time, which means I can just create a list and do, is this less than 2, 1, 1, for instance, which is true. I can just use the comparison thing I have on lists of values, since I have it working on anything that is ORed, which will be the case of a list as well. So in the constant case, I can cheat. But I will have to re-implement it in the context of functions. I will not be able to do that. But in the context of constants, I can do that. So that's just going to be a matter of oh, this is tricky. For this, if I find struct expressions, I need to resolve the struct type to be able to figure out the order of the fields. Unless for struct expressions, I always reorder the fields to be correct so that I don't have to do it here. Which I don't do at the moment, but I do here have the fields info, so I could do that. But do I want to do that? I don't think I want to do that. Because if something panics in the struct expression, I think I want the fields to be evaluated in the order in which they appear in the code. I don't think I want to reorder the order of evaluation of the fields, because otherwise I could be introducing some panics in places where that would be wrong. I don't think I can arbitrarily reorder things. I mean, in theory, I can, right? Because there is no way that the field expressions for different fields in the struct depend on one another. So, in theory, I could decide that the language does not guarantee that the order of evaluation of those things will be. But at the same time, if it's a function call for each of them, that might perform side effects. No, I can't reorder the order of the fields. That means that my struct comparison expression will need to do the comparison in the right order, and that means I need to have access to the struct info. However, before I do that, excuse me, let me check something real quick. I was checking the behavior of struct comparison in Haskell. Let's have a look at struct comparison in Rust, and let's see if there's anything different. If I have a struct foo that contains an x, which is an int, and a y, which is also another int. Thank you. Let's see what happens, and I derive partial equality, partial ord, and ord. Let's try things. Let's have, excuse me, let me just check whether this is urgent. Okay. So let's try. I will want to try is foo x4 y6 less than foo x5 y5. What are the semantics of struct comparison? The answer is true. And I assume that those are not based on the order of the field. So if I change this here and y first here, okay, still true. So the order up is done in the field order here, not in the way they appear in the struct expression. That is what I was expecting. However, if I have a function error1 that gives me an int in theory, but in practice panics with O knows 1. And we have another one that does the same thing but called 2. If I try to create a foo thing in which y is error 1 and x is error 2, I expect this to fail with error 1 because I expect the fields to be evaluated in the order in which they appear here and not to be evaluated in the order in which they appear in here. So this should err with error 1, not error 2. What is wrong here? There's a missing parenthesis here. And a semicolon missing here. Unused variable, okay. Oh, knows 1. Okay, so indeed, the fields are evaluated in the order in which they appear here. So I cannot do reordering. I mean, if I want to keep the same semantics as Rust, which in this case I would like to, I can't do reordering of the fields. But when I do the comparison, I need to do it in the order in which the fields are declared, which is the worst case scenario in terms of implementation for me, but that's fine. That means that here in this context here, I can't sort the things based on their name. I need to look up the struct info. And I need to have a look. I need to have access to. I need to have access to the struct info to be able to do that. Okay. That's going to be annoying. That's fine. Because this just means this is now a thing in the analysis monad, which means this is now this, which is fine. Those are all pure of this, which is fine. And this is now a do block. Why was this a do block before? How was it a do block despite being... I guess if I don't do anything monadic, do is fine. Yeah, I guess. Since it's just syntactic sugar, if I don't do any operation that requires inlining into a monad, that's fine. It doesn't need a do block can exist for something that's not a monad, I suppose, yeah. That's fun. I wonder if it's because I have applicative do enabled and therefore do is a bit more, or if this would work actually without any... No, I mean a normal GHCI, not stack GHCI, so no. Okay, well, today I've learned. Okay, so here, what I need to do is I have the name of the struct. I know for having done this type matches here, I am in the context of a constant where type arguments don't exist, so I know that these two struct types must be the same. So I should be able to do a lookup. Context, where are you? Is it check struct? I think it is. Takes a path info resolved and gives me all of this. Okay, perfect. And gives me, okay, I don't care about the hash map identifier thing because that's purely tells me what the type mapping is. that I don't care because I've already done the type checking at this point. So here I can do a struct info and I ignore the mappings, which is the result of doing a check struct type from the type struct type here. And I'm going to rename this left-hand side fields, right-hand side fields. I think this is a better name. So I check the struct type here, which should give me the struct info. And if it gives me nothing, something went extremely wrong because it's not supposed to happen in the context of a function, I can do an error ice here for now. This will be at some point replaced with a proper, the compiler panicked due to an internal logic error. This is an internal compiler error. Please report it here. But for now, I don't have proper error handling. This is just a panic. Okay, so now we have access to the struct info, which is this thing, and I care only about the name of the field. So that's going to be this non-empty thing called struct values, and I need the first thing, which is the identifier. Okay. Here, I'm gonna cheat again. I'm not gonna re-implement a generic, like a thing where I check, are those two first equal? Is that not enough, like for like inequality comparison? I am just gonna generate a list, a non-empty list of values, basically, for each of them and use built-in list comparison for them because I know all of the values at compile time by definition because I am in a constant and therefore I can always get... Yeah, I can do that, I think. Wait, no, I cannot do that. Unless... Give me one sec to think about this. Give me one sec to think about this. Because if I generate the list in the proper declaration order of the fields on the left-hand side and right-hand side, I can't then just generate... I can't then just do a comparison because those might not always have the same types. So instead, I will need... Yeah, I'm going to have to re-implement the thing where... Which means... If I want to be this to be generic for any operator, which I want to because I'm using it for equal, different, greater than, less than, greater or equal, less or equal, then I need to be able to say, with those two values, do I know enough to decide, or do I need to continue beyond this, basically? And that is different for each operator. Because, for instance, if I'm trying to say A is less than B, and I'm comparing the fields in the correct order, if the two first fields are equal, that is not enough for me to be able to say, is this less or not? I need to go to the next field. So how can I implement... How can I implement this in a generic fashion, basically? I don't know if there's a good way to implement this in a generic fashion. Unless I could do instead. Yes, I think that's the right approach. Okay. What I could do instead is have this function I'm giving here not give me a boolean, but a maybe boolean. And it's basically, if it tells me it gives me a boolean, it means I have enough to answer this. And if it doesn't give me one, it means I don't have information I need to continue. And I need to provide that and a default boolean in the case after comparing all of the fields, I don't have enough information. So basically, is a less than b if I'm comparing two field structs. So basically, a less than b. In the case of equality, I have to say nothing. I can't decide. And then after that, if like I can otherwise, if it's a strict yes or no, I can return the boolean. Otherwise, I have to say nothing. And if all of the fields return nothing, the default value is false because it means they are equal. And if I'm trying to do less or equal, it's the same thing. It's not enough to know with one equality, but the default is true. I think that works. So I need to do this, maybe boolean, and a default case boolean. Okay. So that changes to a maybe boolean here, and a default case boolean here. In the case of the comparison of two values that I know, this is simply a from maybe default case of applying the comparison. However, for two fields, for two structures, I need to go in order of the fields. Okay, so this is going to be in the struct info. If I look at my what's it called again in the AST? It's called struct values. That thing is it is a non-empty list of tuple field name field type. So what I'm going to do on each of those, I'm going to do a map. It's probably going to be actually, it is foldable, right? Traversable is actually what I want. It is foldable, traversable, perfect. So I can get my non-empty list of comparisons. So comparisons will be a 4 on this, and for each field name and field type that I ignore, I will perform a monadic expression. So that's going to give me a monadic non-empty list of whatever the result of this is. And that monadic expression will be doing a compare expressions using the same operator default case on two expressions, which will be the expression for that field in the left-hand side and the expression for that field in the right-hand side. So left-hand side field, right-hand side field, where both of those are going to be a lookup in, so it's going to be a find. I already do this in field access expressions. There we go. So I can do this. Actually, let me check something. I do this for a field. So that gives me the field, so that gives me the name and the value. So I want indeed this second thing, which will be a typed expression. You have opened a can of worms that you do not realize. I'm looking at the time. How long do I want to spend on this? I have recently actually opened a thing, and I want to actually reopen it because it was a success, where for 2 weeks I volunteered. I had a calendar open. You could book 30 minutes of my time, and I would explain to you what monads are, trying to dispel the myths around them. I volunteered my time because this sentence that monads are just... Well, yeah, I'm already on the record on this several times, but I'm happy to do it. This sentence that monads are just monoids in the category of underfunctors is, simply put, wrong. So, okay, let me see if I have... Do I have the slides somewhere? Can I go through the slides? I guess I could just like do a recording of this and let's go. Or do I do the short version, or do I do a Haskell-specific version? Let me see. I should have a slide somewhere. If I go to... Is it called presentations or slides and everything? It's called presentation, yeah. Okay, and I go to this one. And I put that in full screen. Let's go. With still my face on it. Let's go. I'm probably going to clip this afterwards and put it on YouTube once and for all. But yeah, very, very quickly, let's talk about monads then, since the question was asked. And because this is the hill I want to die on. So, very quickly, this presentation was like no Haskell, no category theory, almost no code. And the way I was giving it, and again, I'm probably going to reopen this at some point because it was a success, was 30 minutes, give you an intuition for what monads are without using any of those things. Here, we'll probably switch to Haskell afterwards because there's a lot of things that are Haskell specific. But the gist of it is basically that the monads that we use in programming are not the same as the monads we use in category theory, because one is a mathematical object and the other is a programming idea. They share the same name, but that doesn't mean they're the same. What I mean is, look at functions, for instance, which is the only math that there's going to be on the slides. Here on the left, you have a mathematical function, which is slightly truncated on the stream, but you can see what it is important, which is it's a function from a value in its domain, n, the set of all integers, to a value in its codomain, the set of all integers n, and to an integer x, it associates an integer x plus 1. And here on the right, you have a C++ function that takes no arguments, written no value, performs side effects. Those two things are different. We call both of them functions because, you know, clearly the ones on the right, the C++ one, were inspired by the ones on the left, the mathematical ones. But clearly, they are different things. The definition, the mathematical definition of a function will not apply to a C++ function, and a C++ definition of a function will not apply to a mathematical one, because those things are different. Side effects makes no sense in the context of a mathematical function. Limits or whatever make no sense in the context of a C++ function. So, while those two things share the same name, we accept pretty easily that they are different and that their definitions do not match. The monads of programming are not the same as the monads of category theory, and their definitions do not align either. The sentence, monads are just monoids in the category of underfunctors, might be true for the monads of category theory. I don't know much about category theory, but my understanding is that it's not technically correct. It's slightly incomplete. But I can say for sure it is not true about the monads of programming, because they are different. So, the way I structured this presentation originally is like I go through two very basic concepts to then explain monads using those concepts. Like, again, not going deep into implementation, just like very, very high level. What are they? What purpose do they serve? Part one was about interfaces or traits, prototypes, abstract base classes, type classes, however you want to call them. The idea is this, you're probably already familiar with this. Sometimes we have the same behavior across a bunch of different types. We can name that behavior, extract it, and put it into an interface or trait or type class or whatever you want. And that defines kind of a contract. A type is a valid instance of that interface if it implements the contract, the functions in that interface. The most classic example I could think of was the Java one, slightly simplified to fit on the slide, which is, yeah, serializable. A type is serializable if it implements this. Some languages don't have interfaces or prototypes, or I discovered that Swift has another protocols, I think is in Swift, or type classes or traits or whatever. Like Python and C++ have this notion of abstract base class, but that's kind of the same idea. It defines a contract, right? So the goal of interfaces, traits, type classes, however you want to call them, is you can write generic code. You can write code that serializes a container regardless of the actual type of the things within, because you can do that as long as the values within are serializable regardless of what their types are. You can write generic code. That's pretty great. But some languages go beyond that, and yeah, exactly. Golang has interfaces, but its implementation is like, as long as the type implements the correct thing, you don't have to explicitly say that. But yeah, that is the same logic. Allows you to write generic code, great. But some languages go a tiny bit further, and they extend the language itself with some interfaces. For instance, in JavaScript, the language is aware of the thenable prototype, and that is basically the one from promise, because historically there has been a lot of different implementation of promises that all shared the same thing, which was that they had a then function, and therefore we give a name to all of those things that have a then function, which is thenable, and the keywords await and async in JavaScript are defined in terms of, yeah, they work for any type that is thenable, any type that has this thenable prototype, any type that provides then. In C#, you have this enumerable class interface, which is like this type contains value that can be enumerated. If a type implements enumerable, it is compatible with the for each keyword of the language. Rust also famously makes use of that, of using traits to extend the syntax of the language. Try is the trait that provides the question mark operator. Send and sync are also known by the compiler and relate to like async programming and so on. So again, very basic stuff. If you have implemented anything in any language, this notion of like interface, trait, type class is something that you already know, right? Nothing too complicated. But again, the interesting part is some languages use it to extend the language itself. The second part that I wanted to talk about to then give an intuition for monad is a specific pattern that shows up across a bunch of different types in a bunch of different languages. And that's the and-then pattern, also known as flat map in some contexts. The gist of this is you need to know about callbacks, but most languages do this. This is a very, very abstract example in Go, where you define callback as being functions that take a string and perform some side effects. And here's an example where we have a function that fetches something to the database and takes a callback as an argument that will presumably be called on the result of the fetch. This kind of like we give a function as an argument to another function happens a lot. Here in Python, we are giving a lambda to a filter, so filter takes a function as argument and will call it on some values. Callback functions as arguments, again, I assume not any problem there. Where it is interesting is when it's used like this. This is the and then or again, sometimes known as flat map pattern, when we have a series of steps. You have a series of steps in the computation where every step does not return a value directly, but something that wraps the value. If each step, step 1, step 2, step 3, return a value directly, you could call step 3 of step 2 of step 1. But here, each step does not return the value directly, but something that wraps the value, which means that at every step, you need to handle the wrapper. For instance, if it's an error, you need to handle the error before getting the value to then continue. Or if it's a promise, you need to wait to get the value to then continue. So a lot of types provide this and then thing, which allows you to give the callback to then just like give the next step. Crucially, in almost every case where this pattern shows up, it is the same type at every step. For instance, in JavaScript, it is like promise is the go-to example. In JavaScript, if you do a fetch, this fetch does not block. It returns to the caller immediately. It doesn't wait until the fetch has succeeded to give you an answer. But if it returns directly to the caller, what does it return? Because the fetch hasn't happened yet, right? Well, it gives you a promise, something that wraps the actual result and will contain the result eventually when the fetch has succeeded or failed or whatever, but like will contain the value at a later point. How do you use it? Well, you can just await. You wait for the promise to be finished, and that will yield you the actual value. But again, sometimes you already know what you want to do afterwards, so you can do then. You give a callback that itself returns the next promise, and as a result, you build a series of computations where every step takes the value, returns the next promise, and so on. The result is a promise, and you can await that. This pattern of then and then flat map shows up in a bunch of different types. And again, it shows up like not just for like promises, it shows up also for like things that handle errors, for instance. You might know the option type. In C++, it's called optional. It exists since, I think, C++ 14. And Rust, it's option. In Java, it's optional. In Scala, it's option. Like this type exists in a bunch of languages. In C++ and Rust, they call that and then. In Java, Scala, Swift, it called that flat map. But it's the same idea of this pattern. For instance, in C++, here's an example that I've taken from a repo on GitHub, which I think was the one that was used as the proof of concept to add std optional in the language, where we have this getCuteCat function that takes an image as an argument, and each step returns an optional image because each step might fail. So when we crop to cat, if there is no cat in the image, we get an optional that does not contain an image. So we have an optional image. We cannot just apply add bowtie to the result because add bowtie takes an image as an argument, not an optional image. But optional provide this and then thing, and we can do crop to cat and then add bowtie and then make eyes sparkle. At every step, we return an optional image, and optional provides this and then thing, so we can just give a callback to the next step. Here's an implementation of and then on option in Rust. If you don't know Rust, here's the version with all of the type, just more readable. And then is something that takes the self, an option, and f, the callback. If the self contains a value, apply the callback. Otherwise, return none. So that's the shape of this pattern, the and then pattern. We have types that wrap other values, and we want to chain a series of callbacks of steps in the computation with every step returning a wrapped value like this. We can use and then if this type provides it, or again, flat map is on other languages to do this. With those two things, this idea of interfaces, this idea of and then, you know everything you know to understand monads. But before I move on to explaining monads, at this point, there's a question that's often asked when I do this presentation, which is, okay, part one was about interfaces. We find a pattern that exists across a bunch of different types. We give it a name. And part two was about and then flat map, which is a pattern that exists across a bunch of different types. The question that people often ask me is, are there languages that do define an interface, trait, type class, or something for this and then callback pattern? The answer is not really, because in a lot of languages, it's not really useful. Because most of the time when you do this and then thing, like in an optional, for instance, you know what type you're doing this and then thing in. You are doing this on an option or an optional, or you're doing this on a promise. You rarely need to write code that does this on any type that supports and then. So it's not really useful to define a trait or abstract base class or interface for this, basically. In Rust and C++, it's even quite difficult to do so because the type system does not really allow for that, so those languages don't. There is, of course, one big exception, and that's JavaScript. JavaScript has this venable thing I was showing earlier because, again, they have a reason to have it, which is the language used to have a lot of different promise implementations, and they wanted to have keywords that worked for any of them. So they had a reason to abstract over this idea of we have different type that provides the same pattern, which is why they define a trait prototype for it. But yeah, most languages don't bother. But before I move on to part 3, as a side note, Haskell, of course, does have a trait for a type class, which is the Haskell name for traits, for this idea of we have a type that provides and then, but in classic Haskell fashion, it's not name thenable or end thenable or flat mappable. It has a mathematical name. Do you want to guess what the name of it in Haskell is? It's fine if you don't guess. I can continue the explanation, even if your guess is wrong. But do you want to guess how Haskell calls the trait of? Yeah, I think you already know. Don't spoil the answer. Yeah, it's very easy. The name that Haskell gives to the trait of types that provide and then is monad. That's what it is. A monad in programming is a trait for types that provide and then or flat map. A monad is a type that provides and then or flat map. And then flat map is a monadic operation. That's it. That's all it is. If you don't believe me, in C++ documentation, and then is listed as a monadic operation because that's what a monad is. In programming, not in category theory, in programming, a monad is just a type that provides and then. So, why does Haskell make use of them? For the exact same reason as JavaScript, which is kind of a weird sentence to say, but that is basically that just like JavaScript, there are language constructs in Haskell that make use of there are keywords and syntax that can be defined for any type that provides this and then thing. So we define a trait for it at the language level. Haskell makes also use of it beyond that, but that's one of the reasons why it exists in Haskell. It is a very convenient pattern in the language, and we need to be able to define functions that work for any types that provide and then. Therefore, we define a trait for it. That's it. So, if I close this, and if I go at control monad, the actual control monad, not any of the others, this one, and I look at the definition of monad, somewhere below this, where is it? I'm going to look at the source instead. There's a lot of comments. But basically, monad is a trait for a type M for a type that only provides this, which is basically, it's an operator because Haskell is cursed in that way, which is basically just and then. Like it is, you have some value A inside the context of the monad M, like maybe a promise of int, maybe an IO of string, maybe a maybe of user data, whatever. You have a callback from that A to another B within the same monad, and then does the chaining. So maybe is a monad because you can chain computations that wrap the values in maybe. IO is a monad because you can chain computations with steps that return something in IO. That's all a monad is. Now, how does Haskell make use of it? The main thing is, if I open, where do I have a function that's useful? I don't know, let's do a random foo function that's like return some IO int or something like this. There is, again, syntactic sugar in the language that makes working with them a lot easier. For instance, there's this do thing where I can write. The fallback option is not guaranteed. Not all types have that. But yes, basically chaining things. If I go for like a silly example, I could do something like this takes a string and returns an int. And imagine that the function that I'm going to write here exists. Let's imagine that I do, given this is a username. Let's do a lookup user info, which is not a function that already exists, but let's pretend it does with the username, which is going to give me something in IO. And it's going to be something like this, user info. And then I can do, I don't know, lookup next of kin ID, something like that from the user info, which will give me which will do another lookup and give me an IO int. So this looks like imperative code because it is in a do block, but the do block is syntactic sugar in the language. This gets translated into a chains of and then, or flat maps, depending on how you want to call them, because it gets translated basically to this and then from this function that, given the user info, does this, which we can rewrite as and then this. So this, the do block, gets translated into a series of and then, except of course in Haskell, this is not and then, it is this operator. But that's the same logic. So again, whenever you're chaining things where every step returns a wrapped value, IO, future, list, maybe any of those, and you're using and then or flat map to chain functions, that's a monad. That's basically all it is. In Haskell, it's used quite a lot because since Haskell doesn't have mutable data, it is extremely... I am not familiar enough with Gleam and Erlang to confirm or deny. I'll have to check, but possibly yes. The main thing is in Haskell, since we only deal with immutable data, this is an extremely useful pattern and we use it absolutely everywhere. And an example of this is the state monad. What the state monad is, it's basically we are keeping some state around. So if I have a function foo that is a state of int, and what example do I want to do? I could do something like this. Greet, which takes a username and returns some kind of... There's a bit more complex than I would like, possibly. Because I'm stacking monads. Maybe let's not do that. Maybe something like this, which would be a string, which is the result of like, how do we greet this user, basically. But instead of just returning this, we are carrying around a state, which is a monad, so we can do and then. And this state will be an int, which is, let's say, how many users we have greeted today. This function could be written like this, which would be open a do block. We are in our monad, and we can do something like modify, to modify our state, to do +1, and then return something that is format greet, something, the username, or something like this. The gist of this is, here the +1 modifies the state. So here, if we have another function, run program, that will give us an IO int or something, our run program can be, we evaluate the state starting at 0, and the state we evaluate is the result of doing greet user foo, greet user bar, greet user baz. All of this is within the monad, so those are chained and they all return something that happens to be in the state monad. So they are chained properly by calls to flatmap / and then, and at the end, when we evaluate the state, we will get the inner state, which will be 3, because we start at 0 and we do +1 at every stage. So if we translate this back into pure function calls and remove all the monadic stuff, this thing is simply a modify that we chain into something that ignores the argument and does this, basically. So that's how it gets translated. But what is the state monad underneath? The state monad is simply an alias for something that given some state, so state of some state S and some value A, is this type, given some state, given some state, return something that is the new state and the value A. So a state SA, like a state int string, is something that given the previous state gives me the new state and the result. So we could rewrite this greet. If I were to rewrite it without using anything monadic at all, I could rewrite it. So it's a function from username to state int string. So greet a username is gonna be creating a state that given the previous state, which happens to be an int because state here is an int, will do, it will return a new state and the result of my function. And this happens to be, the new state is s plus 1. That's what the modify does here. And format greet username here. So that would be my greet function. But if we were to try to do all three greets like this would be a lot more complicated because I would have to do something along those lines. State 1 is the result of doing greet. Like I call greet on foo, that gives me a state int string. So I have to do a run state to get the inner function, and I have to call it on my state S0. I get my state S1, and I get my first result that I'm going to ignore. So now I can do this, which is run state of greet bar with S1. So I have to do all of the chaining of the states manually. If I were to remove this do block to instead be, you know, a bunch of, this would be instead a let with 0, S2 is this, and S3 is this with baz, S2 in S3, for instance. I have to do all of the state passing myself. But instead, I can realize that every time the state passing is the same, I get the previous state from running the previous thing in my state monad, and I give it as an argument to the next one, which means here this is S3 actually. So I can write an and then function for my state monad, which is just, okay, I have some state SA, I have a callback function that given some A will give me a state SB, which is my new state, and I want that to return a new state SB. How do we define this? So I have my first state A, and I have my callback function F. What I can do is, okay, so I run state of my state A, which gives me a function from state to the new state and an A. And so this is going to be, so it's going to give me the state function, but I can probably do this differently. The result will be a state anyway, and it will be a function that takes some state S0, basically, and given some like run state SA and apply S0, this is going to give me S1 and A. And the result then of this thing will be to do a run state of F of A and apply S1, and I will be getting the S2 and A. So I define this once, And now, since it's a monad, I can use all the syntactic sugar that Haskell gives me. And I can write, instead of all of this manual state passing, I can just write this, and the state is being passed for me by and then at every step, because I have said instance monad state s, where this thing, and then named bind in Haskell, is this. I should check that this is correct, actually. I haven't tried it, but I'm fairly confident this is mostly correct. But that's the gist of it. Basically, we define how we chain the computation once, which is we run the thing, we get the new state, we can pass it to the next thing. And rather than having to do it manually for everything else, now we can just use the do block, and it does it for us. That was the monad interlude. My point is simply this. Monad simply means, monad is a simple trait, type class, interface thing that means this type provides a mean to chain computations, usually called and then or flat map. Most languages don't bother defining it because it's rarely useful to abstract over the notion of I can do and then on the thing. It's rarely useful to do that. JavaScript does it because it requires it for the await async keywords, and Haskell does it because it is a pattern that is extremely useful when we deal with immutable data, and like JavaScript, it also defines keywords of the language and syntactic sugar that uses the fact that, like, okay, it works on any of the types that define this thing. So monads are not monoids in the category of underfunctors. But yeah, that's monads in well, I don't know, 15 minutes? But that's the gist of it. And yeah, I was running for a few weeks a like basically the presentation you've seen without the Haskell code of just like give an intuition for monads. It was a success, so I think I'm gonna reopen it in the future. I just need to actually pay for the booking service I was using because I was using the free trial. And I'm kind of thinking of also reopening some of the Haskell classes I used to teach. But I would need to update the material for that. But if I do that, I'll announce it on Blue Sky and Mastodon. So let's remove all of this and let's go back to what was I doing? I was fixing a bug in the evaluation of comparison expressions in the case of structs in constants. So let's go back to that. It was in this file, yes, analyze const, that was here. There we go, it was here. So I have to do comparison in the order in which the fields appear in the struct, as we have checked for the way Rust does it earlier. No, absolutely. This thing of like monads have a bad reputation and are poorly understood is the hill I will be fighting on for the rest of my life, because a thing that really bothers me. I've mentioned it. I used to teach Haskell somewhat professionally, and I used to teach it to people that were like brilliant engineers, much more advanced in their careers than I was. And what was annoying to me was I would start talking about monads, and I could feel those brilliant engineers tense up because, oh, this is the part where it gets difficult. And I was like, no, it's not. If you have understood the Haskell syntax, which is the hard part, monads are not that complicated. They are a practical programming thing that solves a practical programming problem. If you understand inheritance, monads are a lot easier than inheritance. They're not that complicated. But because of the confusion with the category theory ones that, again, I personally know nothing about, everyone is convinced that, like, oh yeah, monoids in the category of underfunctors, this stuff must be really complicated. It's not. The difficult part about monads in Haskell is Haskell. It's the Haskell syntax, it's operators, it's lambdas, it's all of that complicated Haskell syntax. Well, complicated if you arrive from a language that is very different. But by themselves, not that complicated. So no need to apologize. I love going on this tangent. That's why it's one of my channel perks of like, yes, that's the like you can I did it for free this time, but yes, basically anytime I'm happy to talk about this because it saddens me to see people think that they're not smart enough to understand this, when in fact, it's not that complicated. So here, we are going through the fields of the structure in order. We need to get the field, the expression in the left-hand side, which again, this should be a compiler error because I have asserted that the types are correct, but since I am in a monadic context where I can report errors, might as well report errors anyway, even though this path will never be exercised. That's fine. So that gives me the name I don't care about and the value, so left-hand side field. By doing a find in the fields that were given in the expression. I do the same thing for the right-hand side. And I return a monadic value, which is the compare expressions using this operator and the default case. Yes, that's correct. On this left-hand side field, right-hand side field, that gives me a Boolean in the monad. I'm doing a for, so I'm traversing all the fields of the name of the fields of my structure, so I get a non-empty list of monadic actions. For does the traverse thing for me and swaps. So this results in a monadic non-empty list of Boolean. I do this to get it in my do block. So I get here comparison, which is a non-empty list of Booleans. And now what I can do is I can concatenate it to get the leftmost one. Let's see. I want something, either I want to use the first monoid or I want to use something else. Let's see, I have a bunch of A that happens to be, no, I think maybe is not a monoid by itself. Wait, but I don't have a monoid, I have a Boolean. That doesn't work. That doesn't work. I need this to return a maybe Boolean, and I need to use the default case at the top level. Yeah, because I need to be able to say it depends. I can't decide. It depends on other fields. Yes, okay, that is correct. So this will be from maybe default case here on this thing that gives me a maybe Boolean. I remove the default case from this thing. There we go. So here, I remove the from maybe here as well. This will all return to me a maybe Boolean, and that's fine. So here, when I've done the comparison, this thing is now a non-empty list of maybe values. And what I want is alternative, I think, which I think is part of applicative. Alternatives, yep. That is what I want, because this on maybe, if I open the GHCI, if I have just 3 and just 4, it gives me, import control dot applicative. It gives me the first one that is basically not a nothing, and if I have nothing and just 4, it gives me just 4. If I have nothing and nothing, it gives me nothing. So basically, I want to do that, and I want to get the first non-nothing, the first that gives me a definite answer, and it could be none of them. And now the question is, how do I, and I can use Google for this, if I have something that is an alternative, wait, is alternative on the... Okay, so alternative is something that is on... Okay. So if I have an alternative f and I have a bunch of f of a, how do I get an f of a out of this? This would be a fold of using the operator, but there's probably better to do. I see choice in parsec. A sum is what I want. There we go. If I look at a sum here, foldable t alternative f, given a foldable list of things that have alternative, give me the result. It's just like m sum but generalized to alternative. Okay. So this will do exactly what I want. So I have a non-empty list which is foldable of maybe Boolean. I can do a sum of this comparisons, and that will give me the first non-nothing Boolean if there is one, otherwise nothing. Perfect. Okay. And now with this at the end, I do a from maybe default case if none of the fields in order were capable of giving me the answer that I want. Okay. So now I can go back to this, the comparison expressions, because now this is no longer enough. I am going to need to define what the functions here that return a maybe value need to be. This is going to be a bit annoying. Oh well. I guess for those two ones, it's obvious. It's either equal or non-equal. I don't have this ambiguity of like if a field is equal, then non-equal is false. Like I don't have the problem of needing the maybe for those ones. So I guess for those things, it could be, and I'm gonna make it 0.3. It's just gonna be that. It's like do the comparison, and the answer is just. There's no value for which I need to delegate, and therefore nothing will never happen. So it doesn't matter what value I give as the default. I can just give true. That's fine. Those, however, are the complicated ones. And I suppose, however, what is easy is those will have false and those two will have true. As in the case where we only have equality, we never have enough to decide if something is greater than something else, then false, because we didn't say or equal, and here true, because we said or equal. Perfect. Now, here that means I need to do a comparison, and I need to return true or false based on LT less than greater than, and I need to return nothing in the case of equality, basically. So I can rewrite this as being maybe compare with compare expect. Okay. And now I just have to define this compare expect function, which I'm going to define here. Compare expect. There we go. Which will take, I never remember the name of that type, ordering. It will take two values of type A, regardless of what they are. So this will be So I need to guarantee that they have ORed, however. And this will return a maybe boolean. And compare expect positive case, I suppose. Will of two values x and y will be case of compare x, y of. If it's equal, then I return nothing. That's the case where we cannot decide. If otherwise, it is some ordering O, then we return just O equals the positive case, basically. So if we're expecting greater than, then if this O was greater than, then it's true. If it was lesser than, that's false. And we have handled the maybe case. Okay, so that should fix the constant thing. We still haven't finished doing the function thing, but we should try to compile what we have made so far so that we can try to see if we have fixed the problem for comparisons. So I will need to comment a few things. I am going to comment out all of this, I think, because that's the thing I was working on that I am not completely sure works yet. So all of that goes away for now. And now let's try to compile what we have done this evening. Okay. Oh. Oh, lens defines a dot dot dot. I didn't realize that. Let's remove it from this. Hiding dot dot dot. Thank you. Field in scope. Okay. Yes, it's called field name in this context. Field name. Field name. Field name. Field name. Just recompile. See what else is broken. It's not named fields here because I'm doing a find on the LHS fields plural and right hand side fields plural. Okay. Default case is no longer an argument to this function. Resolve struct no longer exists. And is resolve struct type, I believe. If I check resolve struct in the case of a constant, yes. Excuse me. Okay, Go doesn't exist here because we are in a different function. It's called analyze function expression in this one. Okay. Couldn't match. Typed expression. Where is this? Oh, yes, this is not pure anymore. Which, of course, is going to be broken in so many subtle ways. Okay. Of course, here, when I find the fields, I have a typed expression which contains their type, which I'm ignoring in this case because type checking has already been performed, which means I need to get the actual value of the fields, like so. Okay. Expected. Oh, here I have subtract. I need to do the same thing of doing pure afterwards. Couldn't match expected type. Oh, how do I deal with this in the context of constants? Let me go back here so I have a bit more screen space. In the context of functions, struct expression. I do from maybe I can do better than this. This is a on nothing m air ice. There we go. However, what does that maybe case mean? Because it might be it's invalid in the context of a constant where we know all the types at compile time. It might not be invalid in the context of a function. So let's have a look at resolve struct type. When does it give us maybe? I suppose when check struct type gives us maybe, which is when we have something that is a type parameter, which in the case of a function is possible. Because, oh, this left-hand side thing is the name, is a type parameter t, I have no way to check whether this is a struct until I know what the actual exact type is, which will be when we actually instantiate the function. So if at this point this gives me nothing, I need to handle this. So I need to do that. Case, if I get nothing, that means I am in the case where I cannot know what the type of that thing is because it happens to be a type parameter, and I can't decide that at this point, which means the result will be it's annoying. I should change resolve struct type to always give me. That's gonna break a bunch of things. This is gonna break a bunch of things. I wanted to do this. Give me always the path info resolved, and then maybe of the rest. Because the rest might not be available, but this should always be. So this is instead pure resolved path and result. Okay, which is going to break so many things. That's fine. It means here that I will always have. Here I have the resolved type and nothing. And I can just return a typed expression, the type of which is the resolved type, and it's the struct expression, which is basically the same. Oh, I can always do the resolve fields first, I suppose. There we go. So that's the case where we don't have the type information. And otherwise we do, and that means we have the resolve type and just this, which means I could instead rewrite this as being struct details obtained by doing this call to resolve struct type of the path. And here I can rewrite this as a simple case of the struct details. And if it's nothing, then I return this thing. Otherwise, if I have just that, then I can do this. Okay. This is going to break so many things, but that's fine. Let's go back to this. Fully resolved type no longer exists. Yes, it's just going to be called resolve type in this context. Wait, I could actually probably make it better if I go back to Here I can probably... Yeah, the only thing I care about is the fully resolved type, which can be obtained with this. I can make this here. And here, that in case of nothing, that's just going to be resolved type. Nothing else is done. In the case where I do have the struct info and the parameter mapping, then this is going to be analyze struct fields. That gives me the fully resolved type, and I can create this the same way in both cases, which is a lot shorter and a lot simpler. Okay. Next. What are you unhappy about? What on earth are you saying? Oh, yes, of course. This must be inside. So this is, okay. So that's the inner expression, which needs to be featured entirely, not just the value. I was decomposing it wrong. So here I just need to extract the type out of it. Inner expression. There we go. What else? Resolve struct type here has changed, because now this is resolved type and struct details. And this tuple is struct details on nothing error, because in the case of a constant, those should be known at compile time. Yep, that should be fine. Analyze function expression E. Oh, right. Yes, this is wrong. Okay, so here I was doing the analysis of a reference expression in the context of an argument to a function call. And I was doing it as like, oh, yes, this is a reference to some kind of random expression. That is not true. References are always to something that is named. So this thing E is not a expression, it is a path to something. So it must always be valid. I don't know how to do that yet. Therefore, for the purpose of testing the changes we have made to constants, I am going to comment this out for now. I'll get back to it after we have finished compiling the rest of this. Resolved expressions. We're still in the end of the function here, so we are almost done. Resolved expression doesn't exist in this context. No, it exists, but it is the wrong type. Okay. Oh yes, same issue where I am decomposing the typed expression and then recreating a new one, but here I am giving only the expression, not the full typed expression, so this is wrong. So I suppose I could just name this as inner or something and give the entire inner thing here. But I don't need the type at all, so maybe I could name all of this resolved expression. And this is therefore the expression type of the resolved expression. But then it appears twice. Maybe this was better like this. And I just don't need this name here. There we go. Okay. And I suppose I'll have the exact same problem here. Okay. Yeah. It's unbearably hot in here. Okay. What are you complaining about? That's probably because this being named must now be surrounded like this, I suppose. Okay. I forgot to make this a do block. There we go. So it was trying to interpret this as being one big expression, and the type was very wrong. Okay. That compiles. Okay, so I'm not going to test the small things we've added to functions today, because I could try struct expressions, I guess. I mostly want to figure out two things. I want to figure out if what happens if I uncomment this. It should no longer be a crash, it should be a divide by zero error at compile time. Let's try that. Parser error, okay. Yes, I forgot something. What did I forget? The semicolon here at the end, I suppose. Yeah, there we go. Now I get an error divide by zero rather than crashing. So this is fixed. Perfect. And now, if I try this broken thing, this should tell me false. No, this should tell me true, because in the declaration order, y appears first, and therefore y being 5 should be true for being less than y6 for this one. So broken should evaluate, well, no longer broken, I suppose, should evaluate to true now. Let's see, in all of the declarations in the top level, broken is a struct definition. Broken is a constant named broken of built-in type boolean that evaluates to true, which is correct. Okay. And now if I try 5, 5, I should get false. Broken is false, perfect. If I try greater than, I should also get false. Broken is false, perfect. If I try greater or equal, I should be getting true. True, perfect. And less or equal, I should be getting true. Broken, true. Perfect. Now, to be complete, I should try with, to make sure that this is working as I expect, I should try with structs that contain structs, basically. So I could try with this s here, I should try to do an s at x is this broken thing, which is no longer broken, but I'm not going to change the name now. So this should still be true. Broken, true. And this should be false. Okay, so it seems to be working recursively as well. So we seem to be good. Okay. Do I have an S1 here that has a second type? I could try with S1, S1. And the X field which comes first is this thing that is always equal, but the Y field is able to differentiate. So let's say A and Y here is B. So this should tell me true. Role not found S1. Oh, did I? Yes, this is commented out. Okay. So I am gonna put it back here. Struct incompatible types. Oh yes, S1 has one type, a type argument t, and both fields must be of the same type. And here I'm trying to create something which is broken for x and a character for y. So I get a struct incompatible type where the type T can either be a character or a broken. So this is like more than one possible type match for T. That doesn't work. I'm gonna call this S2TU, and it's gonna be this instead, where the types can be different, and then it will infer that T is this broken thing, and U is character. So now it should work. Aha. Multiple declaration S2, because I have another S2 here that I was using for something else. This file is a nightmare. The second I am done with the analysis, I can actually write proper tests rather than maintaining this absolutely nonsensical thing. It will be good, because for now this is a complete nightmare. It's going to be S3. Let's go. Okay, now this compiles, and I'm expecting this to tell me true, because the first field is equal recursively, therefore gives me nothing recursively, but the second field, y, actually is, like, it can be resolved, so this should tell me true, and the constant broken there, constant definition broken built-in type boolean, is true, and if I change this to this, it should tell me false. Broken, there we go, false, perfect. And if I do this, it should tell me true again. Perfect. I could actually just like grep broken. There we go, a lot easier. And I should try as well equal equal, which is aha. Aha! That's another bug I didn't anticipate. That's a bug I didn't anticipate. That's annoying. Because here the two fields are equal, and therefore the thing is like, oh yeah, therefore it can't be different, returns true, despite the fact that they are not equal. So okay, let's fix this. This is going to be fixed by changing. Let's go back to constants here. So those are not correct. Basically, when I'm trying to compare for equality, both of those are going to be the same function, which is basically the second any of them is different, that's fine, I get my answer, basically. But if I... In case of equality, I can't decide yet. I need to continue. In case of non-equality, I know that the answer is always true or false. It doesn't matter which one. And the default, if all of them match, will be true for equality, false for inequality. And this is basically, in case of equality, I cannot continue. So it's going to be the same thing as this, except... Okay, so I'm going to change this to be equal this. And this is going to be compare expect. And in the case of I'm comparing for equality, if it's anything else, then it's always const false. And in the case where I'm comparing for inequality, it is const true. Okay, so I can go back to compare expect. Here, which is no longer taking an ordering, it's taking a function from ordering to Boolean. It's always the same thing. In the case of, I'm going to validate, check ordering. If I find equality that's never enough to know, therefore I have to return nothing. Otherwise, I can return just of check ordering of O. Okay, let's try that. Okay, compiled. Let's go back to my main. Let's do instead. I'm not gonna call it broken. I'm gonna call it pair. And let's do const pair 1, which is a pair is this one. And pair 2 is a pair, and it is this one, which is also 5, 5 for now. And let's do a bunch of broken things, which I'm going to rename to test compare, which is going to be a boolean. It's going to be the 1 here, and this is going to be pair 2. And let's do different, less than, greater than, less or equal, greater or equal. There we go. So here, the thing is, every time I'm comparing this S3 thing, and I want to check, the first value is always going to be equal to the other. That's the whole point for now. So it will always differ, if everything works, to the second value, which means this should be false, this should be true, this should be true, this should be false, this should be true, this should be false. Equal equals says false, different says true, less than says true, greater than says true. That's wrong. Wait, no, I'm one off. Equals says false, different says. Oh, they're not in order. They're not in order. Ooh, that's tricky. Okay, so let's rename them. This is equality. This is non-equality. This is great. This is less than. This is greater than. This is less or equal. This is greater or equal. That's the problem of putting it in a hash map. The order is not guaranteed to be the same. So non-equal is true. That's fine. Less or equal is true. That's correct. Less than is true. That's correct. Greater than is false. That's correct. Greater or equal is false. That's correct. Equal is false. That's correct. Okay. And now I think constant comparison of structs is finally should finally be correct. Whew. Which means I can go back. What time is it? I've been streaming for 3 hours. Probably start thinking about stopping for the evening. But we fixed a bunch of things with constants, which is always good. What did we do for functions? Oh, we did struct expressions for functions. So I could try that. That means, in theory, now I should be able to have a function test return struct that takes no argument, or I guess it could take an argument. Let's say it takes an int, and it returns and it returns some pair. And this is a return of pair where x is... Actually, I'm going to use a type alias to make sure that this all works. Type pair alias equals pair. This returns a pair alias. This constructor pair alias, just to make sure this works as well, where x is x and y is 0. Okay. And I can do something else, which is a test runtime struct, which takes as argument nothing, or takes an x as an int, and returns an int, and this will be returning test return struct of x dot x. What I want to check here is, since this... Yeah, I will need to test multiple compilation at this point, and I don't have the infrastructure in place to test multiple module compilation. What I wanted to try was like, oh, this is a function call. I don't have the raw struct expression here. So I can't just like check that the field was given, because unless this is inlined, which is not at the moment, I don't have the raw struct expression, which means I need to do a lookup of the struct info to check this. It would be more interesting if I could do this with like multiple compilation, and therefore try to do something with something where the struct that is being written to me is not in scope. But this is still, I think, a useful test, so we can try that. Can I try something else where... Because here the struct value is known at compile time, I should try to add another function, test return constant or something, which is gonna be taking no argument and returning an int, actually a character. So I'm gonna return this character, why not? And here y is going to be something that cannot be decided at compile time. Well, I mean, could be, but is not. Turn your static constant as int. Okay. So now we have function calls within a struct expression, which is part of the return, which we then use as a field here. This should work, even though none of this can be inlined at compile time. Okay, this compiles, that's good. Let's have a look at... Oh, that's a lot of stuff. I want to look at test runtime struct. There's a function that has one argument, which is x by value of a built-in type int, returns just a built-in type int. The body is a written statement that contains a typed expression of type built-in type int, and the value is a field access expression, that is correct, in which the left-hand side is a typed expression of a top-level declaration main pair. Okay, yeah. And that is correct. The type of the left-hand side is indeed pair. And the value is a call expression of the function main test return struct. That's correct, with no parameters, no path parameters. And then path info x, that's correct. Okay. Okay, that looks correct, I think. Wait. Why is this function argument x? I don't think this is correct. there a warning somewhere? No. Okay. Let me check. What I'm worried about here is I'm worried that this x was resolved as being this x, the argument, rather than being the field x of the pair. So, in this typed expression, the path, the expression value is a field access expression. Oh, no, there we go. The, the field access expression ends up here with the x, so that's correct. That is correct. And the typed expression within is the call expression with the argument call expression and a list then that contains a bunch of typed expression. And the typed expression for the argument is a thing with the type int and the value function argument x by value. Okay. It is correct. So what we've done so far this evening works, which is always good. Whew. Do I want to continue a tiny bit? I might want to continue a tiny bit. We're making progress. It is horribly hot in this. This is unbearable. But otherwise, I can continue a tiny bit. Do I want... Oh, I could try the Boolean negation int negation expressions. Those work. No, thankfully, I live in Ireland, but it's just that I keep my windows closed when I'm streaming, just because otherwise the noise from outside is picked up by the microphone. And having all windows closed, the lights on, and the computers running, and all of that means it is currently... Let me see... Only 26 degrees, could be worse. It's more like the lack of air and all the lights and the 3 screens all on me at the moment, which is a bit rough. Okay, we've tried Boolean negation expression and int negation expression. I could try that in this, where I could do it here where I don't know the value, basically. This should still work. Perfect, that still works, that's good. However, I could try to do it here. And that should bind first, and therefore do minus on the character, and therefore be rejected. Okay, wrong type, expecting it, int got character. Perfect. And I suppose the same thing will be true here, where if I do that, error wrong type, expecting Boolean, got character. Perfect. So that works. Okay, so I think I'd like to make the reference expression work. Because it's going to be an interesting one. It's going to be a very different thing from what we've done so far, given the fact that our type system is not aware of references. This is purely a way to indicate that some function should operate directly on the thing. It's kind of the weird edge case of our weird language. So this should be pointing to something that can be mutated in the scope. Which means it's either... Do I have const in my... Do I have const in my grammar at all? For constants at the top level, yes. Do I have const for, like, function arguments and let bindings? I don't think so. But let's have a look. Where is const used? It is used here for a declaration of a constant, and that's it. Okay, so I don't have a notion of constants in my language. So I don't have to worry about constants. The only thing I need to check for a reference is that I'm pointing to a variable in the scope. that means basically I need to resolve this in the scope. I need to do a lookup in the scope, and I need to check that what I get is not a type, it must be a value, and specifically, it needs to be a function argument at some point. I will have to allow function pointers, but we're not there yet. So it needs to be a function argument or a let variable. If any of those is true, then it's fine. Okay, so I guess the only thing I need, if I do context, okay, lookup role is basically what I want. Yeah, I think basically lookup role is what I want. I could make a more specific function, but it will only ever be used for the case of references, so I can always ever do it here. The only thing is I might want to change my AST, I think. Let me see, in the case of a reference expression, no, I have, perfect, I have a resolved thing. So that's perfect. That means I will need to get something with a role. I guess I could do this resolve expression value, actually. This is actually what I want, I think. Except maybe it's not. It is not. Here I am resolving the actual type of the thing that is being pointed at. What I want here is the actual role of the thing. Ah, but I have it as part of the path expression. No, I can do that. Okay. I can do that. So, okay. Let's go back here. Let's uncomment this. So this is indeed a path. So what I want is to do this is gonna be not analyze expression, but resolve function expression or something. Exp value. Resolve exp value of the path, which gives me a typed expression, which is going to be that. And the result will be I'm gonna have to. No, I can't decompose that. I need to, or rather, I'm gonna do the same thing I've done before. This is inner of a typed expression with the resolve type, and there we go. Except here, I don't care about the type at all. I think I care about the actual. I care about the path expression here. So this must be a path expression, and I must check that the path I get it must be a path expression that contains. Maybe it's not worth doing all of this nonsense then. No, I think it's useful to do it because I will need to type anyway. Okay, so I need to do that. And here I don't care about the resolve type. I cared about the don't care about that. I care only about the resolved value. The result will be pure inner if this succeeds. but I need to check resolved value if it's a path expression with some path info. I can list the cases that are valid. The cases that are valid are this is, look at name. This must be either a function argument or a let variable. So this needs to be a path info, something like this, where this is a function argument. Or a let variable. And in both of those cases, I have nothing to do, so pure. In any other case, I am trying to get a reference to something that's either not the name of something, which, like, is probably like an internal compiler error because I had a path in the first place, or it's something that can be resolved, like it's a constant which cannot be passed by reference, or it's a type name, or something like this. So in any other case, this will be a fail error. And that's an error for which I don't have a diagnostic code yet. Error reference not local variable with the name. No, with the path info resolved. Okay. Error reference not local variable with the resolved value. And otherwise, that's fine, and we can return the inner expression. Okay. Is that okay? Let's try. Okay, that seems to... Okay, it doesn't compile yet. Oh, I know, because... Anyway, it's recompiling things. Okay. I see, I see. The problem here being that this is an expression, and therefore it could be something that is not a path expression at all. Do I want to include... Do I want to include the actual resolved expression in this? Yeah, I don't see the hurt in doing this. So there's going to be an expression... yeah, it's going to be an expression resolved. Yeah, because the type doesn't matter. The only problem is that, hey, this expression is actually some kind of value that has been in line or something like this, not something that can be given by reference. So yeah, the error message can make use of that. Okay. Again. Perfect. So I can try with this done. Let's try to go back to this. I'm going to do the thing as I do sometimes. I'm going to comment all of this for now, just so that I can try something else. I really need to finish this analysis so I can write proper tests. This is a nightmare. What I want to try is this. I want to make a function foo that takes x as an int and y as a reference to int. And for now, there's absolutely nothing I can do because I have not implemented assignment or anything like this, but this should still type check. Now, I want to try a function bar that, given x as an int and y as an int, I don't have let. I can't introduce local variables yet, but I can try foo of return, because return is the only thing I can do yet. So foo of x and reference to y should work. Undefined. So I am analyzing the function arguments, and I got this thing for which I don't have an error yet, which I should fix, where the field is expected to be by reference, and I did not get a reference expression. Huh. Did I mess up something? I did mess up something. That is not correct. I am not returning inner at all. I am returning... No, I am, actually, but I need to type. I am returning a typed expression. Copy this. Where the type is the resolved type, because references are not part of the type system. But this is a reference. Hello, how are you? A reference expression which needs to be persisted, where we have indeed the inner thing here. Okay. So that should be correct now. Except it's not. This needs to be... Oh, yeah, of course. Okay, perfect. So this needs to return to me the path info. So this means that I need the resolved path. And I do that by doing a case on the resolved value. If I get this, there we go. In those cases, I can return the path info because it happens to be correct. I can vertically align this for readability. And in this case, I cannot, therefore fatal error, therefore, okay. And here I now have the resolved path. Perfect. And I don't need the inner alias here. Okay. What am I missing? It's not called, it's called resolved path, just a typo. Okay, and I should probably, while I am at it, go back to this reference expression thing here and actually introduce proper diagnostic there. Where this is, what do I call this? Do I have anything about arguments here in this? Function duplicate arg, I don't. Error function call arg expecting reference. And the only thing I need, I suppose, for this would be what do I have here? I have I don't have the name of the arguments here. I probably want them just for the error messages, which means changing a bunch of things. But yeah, basically, I think I want the identifier here. So I can do a bunch of report here, and at the end of this, I need to do a validate. Okay. Oh, I already have one here. But I think I want to do one here in case any of those is wrong. No, actually, I think I want to only do it here. Ah, no, I think I want to do it in this case as well. Okay. Okay, so here I can do the report, which is going to be error function call argument expecting reference, and that will be the arg name that I don't have in scope at the moment. Expecting value. So if I want to have, I will need to have here arg name arg type. Okay, and that means I need to change one thing. I need to go back to my AST. I need to look at function info, not function info, the other one. Function type here, and the arguments need to be a tuple of identifier and function archetype. Yep, basically the same thing as the arguments here, which means that in my context file, when I'm resolving a function, a partially resolving a function type, I need to make sure that I don't... Here, the resolved arguments, I need to... Yes, this becomes a traverse.traverse of force fun args, force fun arg on this. And now the types should be fine. Okay. But any other place where I make use of the function type will be wrong. But that's fine. We can fix this now. I am stacking so many things on other things. It's fine. Okay. So here... Yes, here this is a case where I'm expecting only the type in the argument, which I don't have. So here I need to do... Yeah, I need to do that to get the actual type. And here I'm going to have the same thing. I need to do a map second on this thing. Okay. Perfect. So now I should have proper errors for this. Let's go back to our test file. I have this function bar calling x foo with x and reference to y because y is a reference. So this should hopefully compile. It does. Perfect. If I change this to be just y, I should get an error, a function called arg expecting reference y. Perfect. And if I give both as references, I should get expecting value for x. Perfect. And actually, if I get both wrong, given the fact that I use the validate afterwards, I should get both errors, expecting value for x, expecting reference for y. Perfect. So that works. And I cannot test with let bindings yet because I don't have let bindings yet. However, I can try if I have a const c here that happens to be an int which is of value 0. If I try to give c to foo as a reference, the type will type check, but however, it will not be valid to take a reference to something that is it's not valid to take a reference to something that is a constant. So I should get reference not local variable. There we go. Now, however, it would be valid to give a reference to x here. And I'll have to think about the semantics of this. If I give several references to the same thing as an argument, it just means I'll have to, in my code generation, make sure the thing is like moved only once. But that's a problem for future me, and I don't care about them at all. So future me will handle this. Okay, so that seems to be working, which is good. So we've added struct expression, reference expression, Boolean negation expression, int negation expression. We fixed the division by 0 being a crash rather than a compile time error. We fixed struct comparison not doing struct comparison in the correct order and therefore being wrong. I guess I could stop here. It's been 3 hours and a half. But I guess I could also try to quickly make some progress on the binary int expressions and so on that I was working on earlier. At least if I don't use them, make those things compile. Because those should compile already. Comparison expression is the one that should not compile yet because of the exact issue we had in constants. But those two helper functions, despite not being used, should already compile. They don't. Okay. Yes, resolve type doesn't exist. This is the expression type of the left-hand side. And this is the expression type of the right-hand side. Okay. I suppose I have the exact same problem here, actually. Yes, I do. Okay. Okay. Yes, I'm doing an F map on the result of something. But this F is actually, yes, so this is incorrect. But this is. And I have fixed it here, but I didn't fix it here. Wait, no. No, this was correct as an F map because the function that I give as an argument might fail because I need to handle division by 0. But as a result, pure was wrong. Okay. Defined but not used, that's correct. But they otherwise compile, which means I could copy the ones I have for constants, which are somewhere around here. Well, actually, let's go back here. There we go. And I'm going to remove the comparison ones because those are not ready yet, but I can make use of those two new functions. Here, the comparison expression is not ready, but those otherwise should be fine. Yeah, that should be fine. It's not. Because I'm not giving the constructor. Okay, of course. It's going to be the problem in both of them. And that is simply because in the context of a function expression, I might not be able to resolve the value at compile time, which means I will need to also give what constructor should be used in case we cannot construct a thing. And that happens to be... it's a shame that I'm giving it as a typed expression. Hello, tired, it's been a while, and it's unbearably hot in this room, but otherwise we've made some good progress this evening. Is there a way for me to actually just give the expression here? There's no point. Because I know this is always going to be... This is always going to be a typed expression. This is always going to be a typed expression of type int type with this. So yeah, I can probably do that, which means it becomes an expression resolved. And that means that here, the constructor in question, it happens to just be the one here. There we go. Likewise here, this will be just that one. Okay, and that means here I also need to change this to be an expression resolved. And here to be a typed expression of a Boolean type of this. Okay. And now we can try this. It's wrong. Because I'm an idiot, of course. This is, those are all the same. What I've been missing is those ones, which I'm going to copy from here. Those two constructors. And just so that it looks good, I'm going to align all of this vertically. There we go. Except I'm going to just need to align this and therefore this as well. There we go. Okay. So subtraction is at compile time, if we can resolve, is subtract that we just put in the monad because we don't need to do any error checking. Likewise for multiplication and exponentiation. For division and modulo, we use this thing because we need to check at compile time that the value is not 0 because we don't want to crash. Otherwise, if we cannot resolve at compile time, we recreate the sub-expression with the same constructor, which happens to be this one. Yeah, okay, that should be fine now. Okay. Which means I can test one last thing for this evening, and then I will stop. If I go back to here, If I change this to be returning some kind of int, then I should be able to do x plus 1 equals 2 as int or something like this. Actually, I don't know. I don't remember what the priority of the precedence of this is, so I don't remember if this is going to be correct or not. We'll see. Undefined. I run into an undefined at line 804. Because I did the plus, of course. I did plus and I don't handle plus yet. So let's do x minus 1. There we go. No, undefined still. How on earth? This should be interpreted as a subtraction expression, but it seems to be implemented as something else. Compile first. Is that the parser error? I think I've tried arithmetic expression in constants, right? It's an equality expression. Oh, I don't have those? Oh, no, I don't indeed. That is correct. I don't handle equality expressions yet. I do handle and or, but not this. So yes, I can't do that yet, but I should be able to try. I should be able to do x minus 1 at the very least. Okay, wrong type. Built-in type unit. Huh. Oh, yeah, that's true, yeah. This returns has a value of type int, and this function does not return anything, so that's wrong. So I need to make this an int as well, and now this compiles. Okay, so we do support basic multiplication stuff here on values. That works now. Okay. Okay, so that's, I think, where I'm going to stop this evening. What we have done this evening is we have fixed division by 0 being broken at compile time, which is good. We have fixed comparison on structs, both at compile time, well, only at compile time for now because we haven't implemented comparison on functions yet. But at least now here, comparison on structs is now done properly, as in we compare fields in the order in which they appear in the declaration, not in the order in which they appear like alphabetically or in the name they appear in the declaration here. So that's much better. That's fixed. And also we do the thing where, like, if we're comparing for anything like on equality, we don't have enough information, so we continue doing other fields until we know how to compare two fields of something. And we'll do the same thing for runtime. We'll do the same thing at runtime, where we can try. Basically, we omit all of the comparisons that can be done at compile time until we encounter one that cannot be done at compile time, and therefore we need to continue. Yeah, we can do something smart, but we haven't done it yet. And we've added support for, in the analysis of functions, we've added struct expressions, reference expressions, the Boolean negation, int negation, and some of the subtraction, multiplication, and so on. Okay, Next time we'll do addition, which is missing because addition is complicated just because at some point we'll have to handle string concatenation as well. So we want to do something a bit more complicated than what we do for the binary int expression. And we will want to handle comparison expressions. And then we will have the very difficult task of assignment expressions. But we are not there yet. So that's going to be a problem for later. Okay. Whew. Yeah, I think that's basically it for this evening. I'm going to stop here, I think. Thank you, everyone, for tuning in. That was a lot of progress. I'll be back on Thursday for more progress. In the meantime, I did the call out for this at the beginning. I've joined a small group of people who do streaming in functional and declarative languages. It's the declarative.tv link that is in the prompt here on the left. If you want to find other people who, like me, stream in Haskell and other functional or declarative languages, that's where you can find the list. And we have a small Discord. So if you want to chat about the project off stream, that's the right place to do so. So yeah, thank you everyone for tuning in. I'll see you on Thursday. And now, time for me to go back to GDQ. Okay. See you, everyone.